Hello, everybody. It is Michael Pierce here, broadcasting to you not live this is previously recorded from my cozy apartment, and I have another script for you, kind of like last week. So this will probably be how I'll be doing videos from now on, at least for the foreseeable future, because it's a lot easier. It takes way too long to get all of the pictures together. So anyway, I will be reading you scripts with my beautiful voice and my beautiful face, or whatever. Yeah, so this script I've been working on about as long as I was the last week's script on the criticisms of MBTI. This one, however, is not about the MBTI. This one is about quantum mechanics. So I'm revisiting that. There is nothing explicitly about Jungian theory or MBTI in this video, except at the very end. So I'll probably be splitting this into multiple videos because of the way that my camera records things. So whatever the end of this video or series of videos is where you'll get a little smidgen of Jung. But it probably won't make any sense unless you've watched the rest of the video. So I've caught you. You have no choice but to listen through me talking about quantum mechanics to get that smidgen of Jung at the end. Anyway, sorry, I don't know what I'm saying. Yeah, I don't think I have anything else to start off with, so I'm just going to get into it. Hope you enjoy. I enjoyed writing the script. It's been very enlightening for me, I think. So anyway, introduction. A while ago, I made a series of videos summarizing my research into relativity and quantum physics, or the new physics, as it was once called, and that is the name of the series. I would suggest giving that a watch before you jump into this video, if only to make sure that we're on the same wavelength. It is often said that quantum objects are chimerical. That is, they are paradoxical hybrids between waves and particles. Those are waves and particles. So they're a combination, and we don't know what it looks like. We don't know what that's supposed to mean. Sometimes they are waves. Sometimes they are particles. Don't think about it too much, young student. Well, I have thought about it too much, and sure enough, I take exception to this dismissive attitude rampant in the field. I do not believe that quantum objects are mysterious ontological chimeras between particle and wave. I believe that a much more straightforward interpretation of the evidence available is that quantum objects are simply particles. See, particles. But they are guided by non-physical or ghost waves. My hand gestures making up for the lack of pictures. Is that helpful? I'll stop interrupting myself. This is serious business. Sorry. But no, seriously, that is what I'm thinking, that there are non-physical waves guiding the particles. In contemporary terms, what I'm doing here is I am espousing a non-local pilot wave theory. But in order for that to make sense, we're going to need to do some background. So we're going to cover some ground, but hopefully me covering it in a different way will be enlightening to you. So the double-slit experiment. The chimeric or dual nature of quantum objects is famously demonstrated by the double-slit experiment. Pardon me. When you shine a beam of light through two slits, the two resultant beams will interfere with each other like two ripples in a pond. Consequently, they form a striped interference pattern on the back wall. It therefore appears that light is made up of waves. But if you place this is just one way you can do it. If you place a sort of filter over the two slits so that only a very, very small amount of light can make it through, and then you place a photosensitive plate against the back wall, what would you see on that plate? You would not see a much fainter interference pattern, which is what we would expect if light were really waves and had this continuous nature to it. Rather, you see individual sparks of light on the plate, little specks that come one after the other randomly, kind of like a visual Geiger counter. Light now appears to be made up of individual particles, or photons. But then, if you track where each photon hits the plate, and then let the plate just sort of sit there for a while, building up photon marks, what do you get? You get the interference pattern, just as from before. Hence, the paradox. Light comes in individually wrapped packets called photons, but these photons are somehow able to coordinate their movements and flock as though they were waves. And they can do this independently of each other, regardless of separations across space or time. That's why when you put the filter in front and you make it so that only one photon gets through every hour or so. So they're separated by distances of an hour or days or however long you want. If you just let that pattern build up, it will build up. It doesn't matter how wide it is, how wide the difference in time is, it will build up. That's where the weirdness comes from. How are they coordinating their movements so that they would land and form this striped pattern? The weirdness of this will be more clear if you watch the new physics videos and see me go into it in more detail. But for now, this is what we're working with. So the great riddle of quantum physics, if we wanted to condense it down to just one riddle, is this. What happens to quantum objects in transit between emission and measurement? What are they doing? What is their trajectory? How do they end up where they do? Two interpretations. The interpretation prevailing in universities at the moment is basically non-interpretation. Shut up and calculate is the mantra. This is unacceptable, not only because it betrays the spirit of science, but because it ignores the interpretations of its predecessors, most notably Niels Bohr. In Bohr's view, quantum objects and/or their properties simply do not exist as such in transit, but are brought into being by the act or process of measurement. In other words, while in transit, quantum objects are in a superposition of potential positions, none of which have become actual yet. This superposition of possible positions can be treated like a wave until it hits the photosensitive plate. At that moment, the wave spontaneously collapses into a specific particle with a specific position. And this position is actualized at random. Somehow, interaction with the instruments of measurement, such as a photosensitive plate, forces the indeterminate wave blob to become determinate and collapse from superposition into position, from generality to specificity, from possibility to actuality. Again, the position thus actualized by the quantum object is a matter of pure probability, and the distribution of probabilities may be calculated via Schrödinger's wave equation. If you want an image, it's kind of like if you've ever seen those sea anemones that sort of spread their tentacles out, but then if you touch one of the anemones, it goes shoop, back into itself. It's like that, except there isn't a single point that it all goes back into. It randomly all shoops into any single one of its individual cells. If that helps, hopefully that might just sort of confuse you more, but I'm just trying to provide an image so you see kind of what they're imagining here. Anyway, so this picture, needless to say, did not sit well with a number of Bohr's contemporaries, most notably Albert Einstein. It seemed as though Bohr was settling for an incomplete, merely probabilistic model, rather than pursuing the matter to the end. Rather than search for a hidden factor that could account for each particle's trajectory individually, he had created a weird probabilistic ontology of particle waves that jumped between probability and actuality for some reason. Pardon me. He was doing metaphysics, not science. For example, a counter theory to Bohr is called the pilot wave theory. It posits that quantum particles are always particles, but they are guided by an underlying wave that accompanies them everywhere, much like a droplet of oil bouncing on a surface of water. The pilot wave represents the hidden variable which Einstein insisted must be there, as opposed to this weird ontology of the pure probability state. By the way, as a side note, I consider the many worlds interpretation as ultimately just derivative from Bohr's view, because all it does is redescribe the probability state as being the existence of parallel universes. The random and inexplicable jump between probability and actuality remains unexplained. That's my hot take on that, I suppose you could say. People still say hot take. I feel like an old man. Anyway, the EPR paradox. Einstein and two colleagues named Podolsky and Rosen formulated a famous paradox meant to show the absurdity of the pure probability state and the need for a hidden variable to complete quantum mechanics. Suppose that you take two particles, boop, 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 like so, and you submit them to a process which entangles them. The way this is usually done is apparently called spontaneous parametric down conversion. And this, as I understand it, consists of shooting a laser into a special crystal which splits the laser beam in a very specific way. The two resulting beams are considered entangled, which just means that they are complementary. If you know the direction or energy or certain properties of the one beam, then you can deduce all of that about the other. Why? Because they both came from one original laser beam, and the two beams that split have to add up to the total energy and vectors of the system as a whole. No extra energy has entered the system. All we've done is divided the total energy between two beams. So you measure one beam, you know stuff about the other beam, and if you measure a particle in the one beam, you know something about its corresponding particle in the other beam. They have to complement each other in their properties, their direction, their energy, their angular momentum, etc., etc. As you can probably tell, I do not understand all of the technicalities of this. I know there is more complexity, but that is the essential. I don't think I need to know those in order to make the points that I want to make. So I'll be interested to know whether anybody in the comments is able to say, well, you missed this part and that destroys your entire theory. I hope that's not the case, but there's no way to know because it's very difficult to digest all of this. But I'm pretty sure I have the essentials correct. So anyway, this is the way that we produce two entangled beams of particles, or for our purposes, we're going to say two entangled particles flying off in opposite directions. Then we post a measurement station in each beam's path, which measures the particles at the exact same time to see if they do indeed complement each other in conformity with the conservation of energy. For a classical physicist, this seems redundant. There's no paradox here. There are two particles or beams of particles with complementary trajectories. They flew through space and we measured them, and lo and behold, they were indeed complementary, because how else could it possibly be? But for Bohr, as Einstein points out, this is a serious problem, because for Bohr, there aren't any particles until the measurement occurs. Up to that point, they are superpositions or probability waves, and it is only at measurement that they actualize their properties at random according to the type of measurement. But if that is literally true, as Bohr seems to think, then why does spontaneous parametric down conversion work? If the particles do not have definite properties until measurement, then why is it that the properties of entangled particles are always complementary? When we measure one particle, does the other particle somehow know that its twin is being measured and can then compensate it perfectly, instantaneously? How does it know what its twin picked if the measurements happen at the exact same time at a great distance from each other? If they send some sort of telepathic signal to each other or something, then this signal cannot travel faster than light, but we need a signal that can reach the twin particle instantaneously because they were measured at the exact same time. You see where we're getting with this? Well then, Bohr, Einstein, hypothetically says, are there influences in the universe that transcend spatiotemporality, that go faster than light speed, that happen instantaneously? Or isn't it more reasonable just to assume that the two particles were always particles with definite properties and that their odd behavior is due to some hidden variables like a pilot wave, which we have yet to discover? All right, locality. It is important to note that the EPR paradox is not all that different from the central question of the double-slit experiment, which is how are the particles coordinating across space and time? How does one particle know what the other particles are going to do so that it can position itself in accordance with the laws of physics, i.e. Schrödinger's wave equation. The purpose of the EPR paradox is to prove logically that Bohr's interpretation is not the last word, that the probability wave is not a real phenomenon, but only a handy mathematical construct, which was originally how everybody considered it anyway, and that there must be some physical hidden variable accounting for the particle's trajectory. But there is a chink in the paradox's armor, and this is the assumption of locality. Locality just means that there are no influences, forces, or effects that can exceed the speed of light. Everything is slower than the speed of light. All effects are bound by locality. Nothing can happen instantaneously. Things can happen simultaneously, because that's no problem, but an effect cannot have, a cause cannot have its effect instantaneously. It has to travel across space-time to the location of the effect. So, if the sun explodes, the effects of this event cannot be felt on Alpha Centauri for at least a year or two, when the light finally traverses the distance to get there. There are no truly instantaneous effects. Everything takes time, and everything must cross space. The upshot of this, by the way, is that all forces are necessarily contact forces. That is, they make their influence felt by proximity, by local contact, by touching the subject of their influence, by intersecting in space-time, if that makes sense. That is locality. Thus, the EPR paradox centered the riddle of quantum mechanics around one question. Is the universe really local, or are some non-local effects permitted? If they are, then Bohr stands a chance of being right. But if they are not, he's dead in the water. There's nothing he can do. The Bell test. Enter John Bell. In an attempt to vindicate Einstein against Bohr, he devised a way to make the EPR paradox into a real experiment. Up to that point, the EPR paradox was viewed as a problem for philosophers, not physicists, because regardless of whether Einstein or Bohr was right, the phenomenon would be the same. Entanglement works. But Bell figured out that their views, Einstein and Bohr's views, really did imply testable predictions. Though it is somewhat tricky to explain, it's easy to lose track of what the experiment is really for, I found. But once you get it, so what I'm going to try to do is I'm not going to explain the exact experiment itself, which I attempt to do in the new physics video. You can go there for more details, and there's other resources on the internet you can check. But what I want to do here is to get at the essence of what is actually going on by presenting two different experiments. So let me show you what I'm talking about. So if Einstein is right, then particles have definite properties all the time, and these properties are determined by entanglement, in the EPR paradox anyway. They're determined at the moment of entanglement, and they remain the same until they're disrupted by some external force. For Einstein, the interesting part of the experiment, therefore, is that moment of entanglement, because that's when the particles, as it were, divvy up who gets which properties, and then they go off on their ways, and everything else is just fine. It's that moment that is important. So, if Bohr is right, on the other hand, then particles do not have definite properties until the apparatus of measurement draws the properties out of them, as it were. Thus, for Bohr, the interesting part of the experiment is not the entanglement, the moment of entanglement, but is the moment of measurement. And that is when somehow the particles divvy up their properties instantaneously across space-time so that they are in coordination with each other. Now, let's imagine the Bell test metaphorically from Einstein's point of view. Say there's a man in Colorado. It's a state right in the middle of the United States. That's why I chose Colorado. For those of you who don't live in the United States and don't know what the heck I'm talking about. So he lives in Colorado, and he rolls in his house a single six-sided die. In fact, you know what? Let me pause the video and get a six-sided die just so you see what I'm talking about. All right, I'm back. I have a six-sided die here. You can barely see it. There's the camera. See, look, it's a die. So imagine this die in your mind when I'm talking. So he rolls the six-sided die. Can you hear that? That was me rolling the six-sided die. Then, on separate pieces of paper, he writes A, which number was facing up, B, which number faced north, and C, which number faced west. Because when you roll the die, you have the side facing up, and then you have these four sides around, so he's limiting it down to three sides. The side which is facing up, the side which happens to be facing north, and then the side that happens to be facing west. That's right. So he places these numbers in separate envelopes, and they are labeled, by the way, A, B, and C in correspondence. A is up, B is north, C is west. Great. He writes those, puts those in envelopes, puts all three of those envelopes in a bigger envelope, just so they're all together, and then he ships that bigger envelope off to New York, which is on one side of the country, for measurement. He does the same thing for the opposite numbers. So the number that is facing down, the number that's facing south, and the number that's facing east, and he places those in corresponding A, B, and C envelopes, puts that in a bigger envelope, and ships it off to San Francisco, which is on the opposite side of the United States, for measurement. Hopefully you see where I'm going with this. He's effectively, what he's done is he has written the specifications of an entangled particle, which is represented by the die, and he has put the answers at the beginning. The answers were determined in Colorado. He's put them in envelopes and he shipped them off for measurement. So what do you think is going to happen? Each measurement team, once they get the envelope in New York and in San Francisco, each team chooses at random one of the three envelopes they received, A, B, or C, to open up. And then they simply record the number that they found inside. And that is Einstein's version of how the experiment works. Hopefully that makes sense. So you see that the New York measurement station could choose the A envelope, and then let's say that number is 3. The way that the dice works is that whenever 3 is always on the opposite side of 4. So they could deduce that the envelope that is in San Francisco, the A envelope in San Francisco must have the number 4 because it was this dice. You see where I'm going with this? However, the San Francisco lab could very well have chosen the C envelope. And so then and who knows what's in the C envelope? It could be 5, 2, 6, or 1, whichever one was facing west or east if it's in San Francisco. Hopefully I'm not overly confusing you, but I think you get the idea. So let's look at Bohr's point of view. So we return to the guy who's in Colorado, who does not, pardon me, let's return to the man who's in Colorado. In Bohr's version of the experiment, this Colorado man doesn't roll a die, and he doesn't even write anything down. He really doesn't do anything. All he does is he takes 3 blank pieces of paper and he puts them in envelopes, labels them A, B, and C, and he ships them off to New York and he ships the others off to San Francisco. Then each measurement team, upon receiving their envelopes, chooses one at random to test. And this test consists of inputting the letter that was on the envelope, A, B, or C, into a special program which is on the internet. The program then assigns that envelope a random number between 1 and 6, which they then write down on the blank paper as though it had been there all along. And they also record what that number is. The program, by the way, links the New York and the San Francisco lab together via the internet, and it ensures that if both teams happen to put in the same envelope letter so that they are checking the same axis of the die, it will ensure that the numbers will match up. So that if they open up the envelope A, if New York opens up the A envelope and they see a 6, that internet program will make sure that whenever the San Francisco team opens up its envelope, it will always be a 1, because that's the only number that makes sense in order to preserve the conservation of energy. And it's the same with the rest of the die. It will make sure everything coordinates, and because it's the internet, for all intents and purposes, it's happening instantaneously. So you see how this sort of replicates the two different visions of what Einstein and Bohr had in mind. For Einstein, the important thing happens in Colorado at entanglement. For Bohr, the important thing happens at the testing stations. Okay, great. Finally, let's say that the measurement teams each send their list of numbers, so they write down every time that they do this. You got the man in Colorado who's just sending out every day a new set of envelopes, and then you have these groups at New York and San Francisco, and they are both checking these envelopes and testing them, and they generate a long list of numbers. Great. So let's say that they then, each team submits their list of numbers to a third research team that's in Australia. Why not? This Australian research team does not know whether the measurement teams generated their list of numbers using Einstein's method or Bohr's method. And this is where we get the actual Bell test. The question is there a way to tell if all you receive are lists of numbers? One list of numbers came from New York, one list of numbers came from San Francisco, and you know that the order of the numbers, it basically creates a list of ordered pairs. So that's what you have. Is there any way to determine whether Einstein's method was used or Bohr's method was used? And that is what the Bell test tries to figure out. So, with that all in mind, John Bell says, yes, there is a way that you can tell. If you assume the experiment runs long enough in order to generate a statistically significant list of data. Let's say that the fellow in Colorado repeats the process well, I already ran through all of this, sorry. I jumped ahead of my script, but let's say that he did this 100,000 times, right? He sends out 100,000 of these bigger envelopes, and so they've generated a list of 100,000 number pairs, and they send that to the Australia team. Well, as it turns out, if you work out the probabilities, which I try to do in the new physics videos, it turns out that if Einstein's method was used, we should see approximately 55,000 of that 100,000 numbered pairs. 55,000 ought to be even odd pairs of numbers. They ought to be alternating, whether they're even or odd. Whereas, if Bohr's method is right, we should only see 50,000 even odd pairs. Thereabouts, around 50,000. In other words, the hypothesis that the particles must be determined along all three axes from the beginning, as Einstein states, that constrains the experimental results in an observable way. On the other hand, if the axes are only determined as needed when the tests are performed, then the skew towards 55% does not occur. It's just straight chance. It's 50-50. The Bell test has been done numerous times under various circumstances, and every single time the results have come up in Bohr's favor. They've been 50-50 with that of the number of alternating compared with the rest. So that's why the Bell test is important, because that's very weird. And we're almost out of time, so I'm going to go ahead and end this video, and I will pick up the next video with probably a much shorter video of my interpretation and my sort of weird theory of what is maybe going on here. So thanks for watching, and let me know any questions you have in the comments below.